HCl, the hydrogen chloride. Okay. So once this HCl dissolves in water, all you have, okay, is H plus and the chloride minus. Okay, assuming today you have 0.1 m. Okay, this is the initial. Okay, you have 0.1 m HCl in your solution. Okay, what's going to happen is actually most of them is going to dissociate. Okay, so assuming okay, assuming you dissociate to this level, so you're going to generate 0.09999 m now H plus 0.09999 m now CO minus. Okay, so when you reach your equilibrium in your solution, you're going to have 0.00001 HCl. Okay, and you're going to have 0.09999 H plus 0.09999 chloride anions. Okay, so apparently hydrogen chloride is a very strong electrolyte once you dissolve in water for most of the time. And you have very limited amount of HCl. Okay, you have very limited amount of HCl. Most of them exist as H plus and CO minus. Okay, so this is definitely a strong electrolyte. So when people talking about a strong electrolyte, the concentration-wise, okay, it's not a concern anymore because if you have that much, you can pretty much say, okay, you are going to have that much H plus and that much of chloride minus. So concentration calculation is not an issue, okay? But so you don't need to actually do the things we just did for the weak electrolyte. Okay, the question people want to ask now is actually, since this strong electrolyte is going to dissolve quite a bit inside your solution, okay, and eventually you reach equilibrium, and in that specific condition, you know you're going to have HCl, vapor pressure, so you have gas phase stuff in the air, okay, and inside your solution you have your HCl, okay, you have this guy, very little amount, and huge amount H plus and Cl minus, right? So people actually is interested in, okay, so how can the concentration of this species related to the vapor pressure of hydrogen chloride in the air? Okay, so the question typically people want to know is actually how the vapor pressure of HCl is related to the solubility of your hydrogen chloride. Alright, so and that's the thing we want to discuss. Okay, so to solve that, we need to know, okay, at equilibrium, okay, now you can write the mu G is going to equals to your mu solution is going to equals to your mu ionic or electrolyte species. Okay, and we will write the mu G is going to equals to mu G now plus RT natural log T HCl over T naught. Okay, and then we will write the mu solution is going to equals to your mu liquid now plus RT natural log A HCl. And for your electrolyte, you will write, okay, this is going to equals to mu plus naught plus RT natural log A plus mu minus log plus RT natural log A minus. Okay, so we know this will be valid because you have three different conditions inside your system, and at equilibrium, the chemical potential of each system should equal to each other. We also know the G, the chemical potential is equal to chemical potential at the standard condition plus some correction terms, right? So for the gas phase, it's P over P naught. Okay, for the solution phase, we use activity. That's why we write the A HCl here. For your ionic conditions, we separate the plus and minus here. Okay, but you can see the general form still mu equals to mu naught plus RT natural A. Alright, so this is always true. Okay, now we can use this, or we can use that to correlate the vapor pressure of strong electrolyte to the concentration of your species inside. Okay, for strong electrolytes, okay, if you want to correlate this to this, it's problematic. Why? The reason is this one is not attainable. Okay, so when we say if you want to measure the mu liquid naught, okay, that means you need to inside your system or inside your solution, the concentration of your HCl need to equals to 1, right? So it's what the is naught means, right? It's at the standard condition. That means you need to have 1 and not HCl aqueous solution. Okay? But because it is a strong electrolyte, there's no way you can prepare this. Because once it's inside the water, you will immediately become this and that. Okay? Therefore, you can never get this. Okay? So, if you want to correlate this to this, experimentally, it's just not possible. Okay? So instead, what we do is actually we correlate this with this. Okay? Because right now you know this is going to give you these two species. So this is actually obtainable. Okay? So we're going to correlate this and this. Okay? So if you write it out, you can get your mu G naught plus RT natural log P HCl over P naught is going to equal to mu plus naught plus mu minus naught. Okay, so I combine the first two terms here plus RT natural log A plus and A minus. Okay. So for the A, I can again express length with gamma plus minus and M plus minus. Of course, right now here it will be square. At the bottom it should be M not square. Okay, because A plus is equals to the gamma plus times M plus. Okay, divided by your M naught. Okay, and A minus is equals to the gamma minus M minus. You don't actually have the M naught here. You don't have the M minus. So it should be like this. So A plus times A minus will be equals to gamma plus times gamma minus times M plus times M minus. Okay, then we'll say, okay, that is going to be equals to gamma plus minus squared times M plus minus squared. Alright? Okay, so let's move this to the left and move this term to the right. So you're going to have mu G naught minus M plus naught minus M minus naught on the left. On the right, you're going to have RT natural log gamma plus minus square, m plus minus square, and then you're going to have, oh no, the things we are interested in is actually this guy. Sorry, we should move into the other direction. Okay, so we're going to move this one to the left, okay? So let's rewrite this, it's RT natural log PHCl over P naught is going to equals to mu plus naught plus mu minus naught minus mu G naught, okay? Plus RT natural log gamma plus minus square and plus minus square, okay? Then we divide the RT on both sides. Then we end up with natural log P over P naught is equals to this whole term divided by RT, okay? And then RT cancel out, okay? And then we take the exponential on both sides. Then you have your P HCl divided by your P naught is going to equals to exponential RT mu plus naught plus mu minus naught minus mu G naught, okay? Plus gamma plus minus square and plus minus square. So it should be, because there's a natural log here, so it becomes multiplies. Okay? And then you move your P naught to the right, you're going to have P H CL is going to equals to the exponential terms times your P naught times your gamma plus minus square times m plus minus square. Okay, so this final relationship, okay, if you want to call it your PHCl to the electrolyte activity. Okay, so with this idea in mind, okay, this should actually give you some hint too, because it actually looks like somewhat similar to the Henry's law, because we say the Henry's law is going to equals to Henry's law constant K times your activity. This is Henry's law, right? Okay. So what people do is actually for strong electrolyte water solution. Okay. People actually group all these terms and make it become a constant K. Okay, so if you do that, you know your P is going to equals to a constant K times, so this is actually equals to your activity square, right? Yeah, so this is for your strong electrolyte water solution. The vapor pressure of your species of interest is going to equals to a constant times the activity square. Okay? Alright, so if you go to page number 13, okay, there will be an example for this. Okay, it says inside your systems you have five and not HCl, okay, and then it gives you the vapor pressure of the HCl is going to equal to 6.97 times 10 to the negative 5. Unit is ATM. He also gives you your gamma plus minus is equals to 2.38. It asks you what is your Henry's law constant K. Okay? And the other question I want to know is actually what is your mu plus naught plus mu minus naught minus mu g naught. So I want to know these two quantities. Okay? So then you need to use this first. You need to use this relationship. Okay? You need to know this is actually electrolyte. Okay? When you read the questions, you need to know whether you have a strong or weak electrolyte. Okay? And this one, HCl is definitely a strong electrolyte. Okay? Therefore, you know you cannot use this equation. Okay? This is not for strong electrolyte. Okay? This is for the strong electrolyte. Okay? So you should have the capability to differentiate what condition you have, and then apply the correct equation for correct answers. Okay, so P is 6.97 times 10 to the negative 5 is equal to, the K is the things you want to know. Okay, and the A is gamma plus minus square times M plus minus square. Okay, so this one will be provided. Okay, then what is your M plus minus? Because it is a strong electrolyte, so what's going to happen is actually this one will dissolve pretty much 100%, right? Therefore, this is the initial. Okay, and at equilibrium, this one will be around 0, and this one will be around 5 and naught. This one will be 5 and naught. So your M plus minus will be just 5 and naught. Alright? So, you know your gamma plus minus is 2.38 squared. Oh, it's not me. Okay. M plus minus will be just 5 squared. Okay. This one, okay, you do have the idea, okay. Don't pretend that you don't know the answer. You should know the answer because it is a strong electrolyte. Okay? So once you have this, then you can solve for your K. And the K is going to equals to 4.92 times 10 to the negative 7. Okay? The unit, okay, pay attention to your unit because the unit here is actually in ATM, okay? So K is 4.92 times 10 to the negative 7 ATM. So this is done. Okay, the K is done. Okay, so how do you solve this? Okay, in order to solve this, you basically need to go back to here. Okay? You know your K is going to equals to exponential RT mu plus naught plus mu minus naught minus mu G naught, okay, times mu P naught. Okay? So what you should do is actually, this is a term you want to calculate. Okay? You know this. You know temperature, you know the R, you know the P naught. Okay? Then you can estimate the term above. Alright? Clear? Yeah, so when you do the estimation, the only thing you want to be careful is actually here, this term, you use what? You use 1 bar. Right? Here, what's the unit of your K? FEM. Okay, so you need to make sure the unit of this guy and that guy, they are the same. Otherwise, you get the wrong answer. Okay, so what you do is actually you convert this one to bar by multiply 1.01325. Okay, because 1 ATM is equals to 1.01325 bar. Okay, so just make sure the unit is correct. Okay, so if you do the calculation, you'll figure out that your mu plus naught plus your mu minus naught minus your mu g naught is going to equals to negative 36.0 kilojoules per mole. All right. So for this electrolyte solution, okay, it is critically important that you can recognize you have strong or weak electrolyte when you see the questions. All right. So you should really do your calculations based on the equation given. All right. So any questions? Okay, if not, we are going to go to our final example for this semester. So we're going to talk about the buffer solution. Okay, we're going to talk about how to calculate the pH values. Okay, and we're going to apply that concept to the buffer system. Okay. Alright, so first question is actually, what is pH? What's the definition of pH? pH is equals to log. Okay, be very careful. Log in a base of 10. Okay, non-natural log is log 10. Okay, what's inside here? So when you learn these things when you are very young, okay, this is how you do it, right? Okay, and now you should know this is not correct. Okay, not this anymore. All right. So let's return you to remember. Okay. And then what? From here to here, this is correct, right? And then what? This is problematic because we cannot determine this alone, right? Because when you have electrolytes, the cations and anions always appear together inside your solution. Therefore, you cannot use this. This is fine, because we just show you that you can calculate your plus and minus without any problem, right? This is problematic. Okay, so this one, instead of using the gamma plus minus, we use, instead of gamma plus, we use gamma plus minus. Okay, and why this is valid? Okay. We know your gamma plus minus is going to equals to your gamma plus times your gamma minus. Right? So you can consider this is this is actually how we write this. Okay. gamma plus minus square is equals to gamma plus times gamma minus. Okay? Therefore, if you want to know your gamma plus, it's going to be equals to your gamma plus minus square divided by your gamma minus. Alright? So since gamma plus and gamma minus is actually the mean ionic activity coefficient, it's the average values. Okay? So when you do this, okay, you can write, okay, this will be equivalent to this. Therefore, even though we write gamma plus here, it can be substituted with the gamma plus minus. Okay? So that means now you need to know, okay, the definition of your pH will be natural log 10 gamma plus minus times your H plus concentration. Okay? Okay, and every single time when you see this gamma plus minus, okay, you need to ring a bell, okay? If I want to get this, I use divided for limiting law. Okay, if the gamma minus is not given in the questions, I need to calculate this one using the divide for limiting law. Clear? Alright, so let's think about the system, okay? HA becoming H plus A minus. Okay? How do you write the equilibrium constant K? K is equals to AH plus minus AA minus divided by the AHA. Okay? And then you can write, okay, this will be gamma plus M plus, and this will be gamma minus M minus. Okay? So if you combine them all together, you got gamma plus minus square times M plus minus square. Okay, and the bottom is gamma HA times your M HA. Okay? For the buffer, what is buffer? Yes, how to prepare your buffer?
We need weak acid to be contributed.
Yes, so pretty much weak acid, combination of weak acid with base, right? So weak acid with base must be coexist inside your solution. Okay, if it's a weak acid or weak base, that means it's a weak electrolyte. All right, so if it's a weak electrolyte, that means your gamma is going to equals to 1. All right, so this one can be rewritten as gamma plus minus square, M plus minus square, divided by MHA. Okay, so that's the equilibrium constant, right? And we also say the pH. Okay, now we can do this. pH is negative log 10 AH plus. This definition of your pH now, right? So AH, okay, use this concept, okay? Your AH can be written as negative log 10. AH will be equals to your equilibrium constant times your AHA divided by your AA minus. Okay, so what I do is actually just rearrange this equation. Okay, so the AH is going to be equals to the K times your AHA divided by A minus, which is this guy. Okay? Alright, so negative log 10 K, what is left? This actual term you should be familiar with because it's the pKa. Okay? So your pKa just make log 10 of the equilibrium constant. Okay, so it's your pKa. And you still have these two terms left, right? So you can, okay, leave it out, then you have the AHA over AA minus. Okay? So here we can rewrite it as pKa minus log 10. AHA is going to be equal to gamma HA times MHA because it's weak acid, so you can write it just as MHA, right? So I'm going to write MHA on the top. Okay, and at the bottom you see this one will be the gamma minus and the M minus. Okay, or A minus. Okay, and then we know we cannot determine gamma minus, right? So we use gamma plus minus for that. Okay? And this will going to equals to pKa minus log 10 times your gamma minus times. So MHA means